Hello and welcome to Step 441 at VCU. In this lecture, we will learn about simple linear regression. So regression is one of the most important applications of statistics, and in general, the idea of creating a regression model is that we are trying to estimate the mean value of a response variable y. So let's say we have a variable y which depends on a set of independent variables, which we can call x1, x2, up to xk. And then the value of y is related to these independent variables. And we would like to come up with a model or an equation that we can use to predict the value of y as the values of these x's change. Here's an example to think about this. So let's say there's a manager of a warehouse who uses automated vehicles, and he might want to relate the congestion time, let's call this y, the dependent variable, to such variables as the number of vehicles in operation and the size of load being moved. So these two variables, the number of vehicles in operations and the size of the load being moved, are independent variables which make a change in the congestion time. Okay, so the congestion time depends on these two variables. So if we can come up with a prediction equation or model that will express y as a function of these independent variables, then we can use this prediction equation to predict the y for a specific combination of these independent variables and use this knowledge to, let's say, institute policies to minimize congestion time. Another example, let's say there's an engineer and he wants to relate the rate of malfunction y of a mechanical assembler to variables such as speed of operation and assembler operator. So again, we are trying to come up with a prediction equation for this dependent variable, which is rate of malfunction, and the equation contains the independent variables, which are speed of operation and operator type. So the models used to relate these dependent and independent variables are called regression models because they express the mean value of this variable y as a function of these independent variable x's. So in this lecture, we will focus on simple linear regression models. So basically we have one dependent variable and one independent variable x. And the type of equation that we are trying to come up with, or the type of model that we are trying to come up with, is a straight line model. It's a linear function. Okay, so here's how we will define the variables. The dependent variable is the variable y, which we are trying to predict. So it's also called the predicted variable or the dependent variable or the response variable. Usually the letter y is used for that. Then the independent variable will be the variables which will be used to predict this y. And if we have multiple independent variables, we can denote them by x1, x2, x3, so on and so forth. If you have just one independent variable, we will use x for our independent variable. Now here's an example. Suppose a developer of a new insulation material wants to determine the amount of compression that would be produced on a 2-inch thick specimen of the material when subjected to different amounts of pressure. 5 experimental pieces of material were tested under different pressures, and the value of x, which is in units of 10 pounds per square inch, and the resulting amounts of compression y in units of 0.1 inch are given. So we have the data. So in this case, our independent variable is the amount of pressure, and the dependent variable is the compression. So we are trying to come up with a model where we can predict the compression for the given amount of pressure. So we will start by collecting the data and making a plot of these values that we collect. So it's a simple scatter plot or scattergram where we have the x variable on the x-axis and the y variable on the y-axis. The idea is we look at the plot to see if a linear model even makes sense. Is the distribution of the data, does it look linear? If it is not linear at all, let's say it's a parabola, then we don't want to fit a linear model. We would rather fit a quadratic model through that. So let's look at the data and see how it looks. So here is the data. We have these values of pressure that were used, 1, 2, 3, 4, and 5, and the resulting compression is given here. Okay, so let's start by plotting a scattergram. So here's the scatter plot. So these are the data points. As you can see, there seems to be a increasing linear pattern here. As x increases, the y is increasing. And so we could try fitting a model here, which is a straight line model. Okay, so the line that we will fit will obviously not be a line which will touch all points. There will be some deviation of these data points from the line that we will fit. Okay, so here's the solution that we will use. We will use a probabilistic model that will relate the y to the x, where we know there is a random variation of the data points about the line. The model that we are using here is a simple linear regression model, which is based on the assumptions that the mean values of y for a given value of x, graphs as a straight line. So we are trying to fit a straight line, and the points the data points that we collected will deviate from that straight line by a certain amount. So some points will be above the line, some points will be below the line. So this deviation, the distance between the line and the data point will be denoted by epsilon. Okay, then here is the predicted model, the model that we will use. It's the equation of a straight line. So y is equal beta 0 plus beta 1 x plus epsilon, which is the random error terms. That's the distance between the data points and the straight line. Beta 0 is the y-intercept of the line. So remember the form y equals mx plus b. So b is now beta 0, which is the y-intercept. M, or the slope, is denoted by beta 1. That's the slope of the line. So our final model will be of the form beta 0 plus beta 1 x. Okay, so this is what we have. So these are the data points. Let's say this is the line that we are trying to fit. Then this vertical distance between the data points and the line is the error term. These are the errors. Okay, this is the slope. For each 1 unit increase in x, the amount of change in y is the slope. And the point where the line crosses the y-axis is the y-intercept, beta 0. So now the problem is, how do we estimate these parameters beta 0 and beta 1 of that straight line? And we want that straight line to be the best fitting line for those data points. So technically we can fit a large number of lines through these data points, but which one is the best fitting line? And that would be our regression model. So for doing that, we will have to base our inferences on the sampling distribution of the estimators of beta 0 and beta 1. And in turn, we will have to check some assumptions about these random errors epsilons. So there are 4 assumptions that we check about the epsilons. And based on that, we can come up with an estimate for beta 0 and beta 1. It is the first assumption. The first assumption is that the mean of the probability distribution of the error terms is 0. That is, imagine this: if a infinite long series of experiments was done, then over time the average of these errors would be 0 for each setting of the independent variable x. But in terms of writing the assumption, we will just use this part. The mean of the probability distribution of epsilons is 0. Now to check these assumptions, we will be using graphs, which will be discussed in the next lecture. But for now, we are just stating the assumptions, and we will come up with a model, and then in the next lecture, we will check these assumptions. Here's the second assumption. The second assumption is that the variance of the probability distribution of these error terms is constant for all settings of independent variable x. So again, here is what we are trying to say. We are trying to say that these error terms have a constant variance, which is given by sigma squared for all values of x. The third assumption is again about the probability distribution of these error terms. These error terms are normally distributed. And the fourth assumption is that these errors are independent of each other. That is, the error associated with one value of y has no effect on the other value of y. So here is kind of what we are trying to say. We are trying to say that these errors are normally distributed with a mean of 0, variance which is constant, and these errors are independent of each other. Now we want to estimate the value of beta 0 and beta 1, assuming that these we don't fail these assumptions. The reasoning behind this method that we will use, this method is called the method of least squares. So let's see, let's go to this slide first. So what we are trying to do, we are trying to fit a line such that we minimize the sum of squares of these errors. So these are the error terms. Okay, so we can call this value y, and this value on the line we will call y hat. So if we take all these distances here, some will be negative, some will be positive. This one, let's say, might be 0. We will take these deviations, square these deviations and add them, and the line which minimizes this sum of squares would be our best fitting line. So if we try to fit such a line, there is only one and only one line such that the sum of squares of the deviations is minimized. So based on this concept, we will fit the line. Now the sum of squares of these deviations, it has another name. We will now call it the sum of squares of error, or SSE. So this line that we will fit is called the least squares line, or the regression line, or the least squares prediction line, most commonly called the regression line. Okay, so here is the idea once more. So we are trying to fit a line which minimizes the sum of squares of errors, and that's only one line that does that. Okay, so for achieving that line, let's see how we will do that. We will need a little bit of calculus to do that. But let's say we have a data point that, let's say that point is xi and yi. So the observed value of y is yi. So this is the data that we are collecting from the sample. Okay, for a given value of xi, the value is yi. Now let's say this is the prediction equation. So if we use this prediction equation and plug in this value of xi, then yi hat will be the predicted value. That will be the point on the line. The difference between these two, the one that we have observed and then the one on the line, is our deviation, or the residual. So the deviation of the ith value is yi minus yi hat. We can plug this equation here, the straight line equation, yi minus beta 0 hat plus beta 1 hat times xi. The hat denotes it's based on the sample. So now so we will have a residual value for each value of y that we have observed. So we have the observed value and the predicted value using the line. So observed value is the point, the data point, and yi hat is that vertical distance, or the point corresponding on the straight line. The way we can come up with the estimate of beta 0 and beta 1 is we will use the sum of squares of deviations of y. So this is the sum of squares of deviation now. So if you look at this, for each value of y from 1 through n, we take all the deviations, square them, and then add them. So this is our sum of squares error. And the quantities beta 0 hat and beta 1 hat, the estimates that we are looking for that make the sum of squares minimum, are called the least squares estimates. Okay, so what we will do is we will come up with the formula for getting these estimates, and then also we will use R or another software to come up with the estimates of beta 0 and beta 1. Okay. To compute the estimates, this is what we do, and we will not see the whole work here, but we will first compute the partial derivatives of the sum of squares error. So partial derivative with respect to beta 0, partial derivative with respect to beta 1. We will set these partial derivatives equal to 0, and that will give us the least squares equation. So if you are interested in how this is solved, please check the textbook. These are the final formulas that we will use. So this estimate of the slope beta 1 hat is given by sum of squares xy divided by sum of squares xx. And these are the formulas for getting these numbers. Sum of squares xy can be calculated either using this formula, which is xi minus x bar, each x minus the mean of the x's, times yi minus y bar. So you take each y and subtract the mean y bar, and then add them. Or another format or another form of the same formula is summation of xi, yi. So each product xy, sum 1 through n, minus sum of all x's times sum of all y's divided by the number of observations. This gives the sum of squares xy, which is the numerator. The sum of squares xx will be a summation xi minus x bar whole squared. So you take each x, subtract the mean from that, square each term, and then add them. Another format that can be used is sum of all xi squared. So you take each x, square it, and then add them, minus sum of all xi whole squared. So basically you add all x's and then square it, divide by n. So these two values, when you take the sum of squares xy divided by sum of squares xx, it gives you the estimate of the slope. For the estimate of the y-intercept beta 0 hat, we will use y bar, which is the average of all y's, minus beta 1 hat, this estimate, times x bar. So these two formulas will give us the least square estimates of the slope and the y-intercept, and we can write it now as the form of a straight line equation. So this straight line is the best fitting line or the regression line that can be or that will be our regression model. Now the next step is to interpret what these two numbers mean, the value of the slope and the value of the intercept. So we know slope is the amount of increase or decrease depending on the sign. If it's a positive value, then it's an increase. If it's a negative value, then that means the value is decreasing as x increases by 1 unit. Okay, so amount of increase in y for each increase in x by 1 unit, that's the slope. And the intercept is the point where the line crosses the y-axis, or in other words, it's the value of y when x is 0. Okay, so for the example, the data that we saw earlier, let's calculate the least square estimates using these equations and then use the interpretation that we just saw. So we had 5 data points, x and y's. Okay, so for sum of squares xy, we start with finding the product xy and then add them, minus sum of all x's times sum of all y's divided by n, which is 5. So when we plug in all values, our sum of squares xy is 7. Sum of squares xx is sum of all x squares minus sum of all x whole squared divided by 5, which gives us 10. So our beta 1 hat is 7 divided by 10, or 0.7. The y-intercept is y bar, average of all y's, minus beta 1 hat, which is 0.7, times x bar. Okay, and then again, when we solve it, we get negative 0.1 as the estimate. So our straight line equation that we fit through this data, the least square line, is y hat equals negative 0.1 plus 0.7x. Okay, and this is the least squares line, which minimizes the sum of squares of errors. Okay, here's the interpretation. Our interpretation for the least square slope it's beta 1 hat is 0.7. That means the compression y will increase 0.7 units for every 1 unit increase in pressure, which is x. The interpretation of the y-intercept, which is negative 0.1, it means that the compression is negative 0.1 when the pressure is set at 0 pounds per square inch. Now, sometimes the y-intercept value may not have a practical interpretation if your x does not expand to 0, but it's the point where the x crosses where the line crosses the y-axis. Okay, so this is what we have done so far. We have defined the best fitting straight line to be the one which satisfies the least squares criteria by minimizing the sum of squares error. And this will be the straight line model. The line is called this least squares line, and the equation is called the least squares prediction equation. Now, most of the times, it's hard to do these calculations by hand if it's a large data set. So we will rely on software to do this. But as you can see in the next few slides, there are different types of regression outputs. We will see where to find the value of the beta 0 hat and beta 1 hat on each of these outputs. So the first one that I have here is a SAS output for linear regression. And this is the parameter estimate beta 0, and this is the parameter estimate for beta 1. So as you can see, it's negative 0.1 and 0.7. Here's what a mini-tab output look like. Again, here are the coefficients, negative 0.1 and 0.7 is for the beta 1. Excel, this is what it looks like in Excel. Again, here are the coefficients. Here's your intercept, negative 0.1, and our variable pressure, which is the x variable, which gives us the beta 1, 0.7 again. Okay. Now, we will use R as the software. I have posted a data set and the R code that was used in Blackboard, so you can check that out. Here is what the output looks like in R. This is the intercept, negative 0.1, and here is the beta 1 value. Okay, and there is a lot of other information that we will be using for the rest of the analysis. Okay, so once we have the straight line equation, we have to now check to see if this beta 1 value is actually statistically significant. We do get a beta 1 estimate, we get a straight line, but is this slope of any significance? So we will conduct a test to see that, and we can conduct a one-tailed or a two-tailed test depending on what we are trying to prove. But the software that we use, all the outputs that we just saw, they have this test for a beta 1 not equal to 0 HA. Okay, so all computer generated outputs will be a two-tailed test where we can test to see if the beta 1 is statistically 0, which means our model is pretty useless, versus beta 1 is not equal to 0. Okay, so we would like to see a small p-value and reject the null hypothesis. Now, this is the test statistic that we use. It is, we use the sampling distribution of beta 1 hat and its standard deviation. but we will just use the test statistic directly from the output, and we will get the p-value from there as well. But it uses the same techniques that we have used for conducting hypothesis tests. It uses a t-distribution with n-2 degrees of freedom. Okay, so we will get these values directly from the output. We will state the null and alternative hypothesis, H0 beta 1 equal to 0, HA beta 1 not equal to 0. We conduct the test only for beta 1. We don't need to conduct the test for the intercept. So from the output, t is 3.66 and p-value is 0.035, which means at alpha of 0.05, we will reject the null hypothesis and conclude that beta 1 is not 0. So what that means is that there is evidence that X contributes to the information for the prediction of Y using this linear model, where we are trying to understand the relation between compression and pressure. Okay. Now we can also create a confidence interval for this slope. So because this is one estimate of beta 1 based on the sample that we have, so we can create a confidence interval for our value of the slope. Again, we can create, let's say we want to create a 95% confidence interval. It again uses this sampling distribution of beta 1 hat and the t distribution. So beta 1 hat plus and minus t alpha by 2 standard deviation of beta 1 hat. Again, let's just use the software. So it will give us a 95% interval will be 0.09 through 1.309. That's the confidence interval for our slope beta 1. Here is the code that I have used to calculate the regression model. So first, read the data in, then you plot to see how the x and y related if it's a linear model. Then data 1 reg, and LM is the function for linear model. Okay, and remember this is y versus x, and the summary of data 1 reg will give the output that we were seeing earlier. If you want to create a confidence interval, you can use the function confint and then bring this data 1 reg here and to choose the level. Also for this, there is a video for regression that is again posted in Blackboard. Make sure you watch that video also. Let me just go back to the output really quick to show you where the test statistic and the p-value are. So here is the estimate for beta 1. This is the test statistic value, and here is the p-value. Okay. Similarly, all other outputs will have the test statistic. So this is the t-stat and the p-value. For Excel, this is where we have for Minitab, test statistic and the p-value for beta 1. And this is where it is for SAS, so p-value and the p-value. So we conduct this test to see if beta 1 is significant and the model, and then that X is providing information for the prediction of the value of Y. So that's all for this lecture. Thanks for watching.